Hey, welcome back to Fat Mama Physics. In these videos, we are going to talk about work and energy. At this point, I expect you to have some understanding of what work and energy is. I will do a quick explanation, and we will get to examples as soon as we can. Now that you're on work and energy, I expect you to know Newton's 3 laws, as well as how that relates to motion. The fact that you have a net force that will cause some sort of acceleration and allow an object to move. So then we'll get to see how that applies to work and energy and how they are related in this unit. So then what is work and energy? To talk about that, we need to have an understanding of how that relates to a system. Imagine you have a system with certain number of objects or an object or no objects. If I do work on a system, that causes the energy level in my system to increase. So imagine that's a bar of energy. Let's say my system, with all that energy, does work on, say, another system. Let's call that system B. What would happen then is that all the energy stored in system A is going to go into doing that work. The energy level in my system A is going to go down to a flat, low level of energy. Okay, so what you see is the interplay between work and energy. Work done on a system causes the energy level in the system to go up, and then energy in a system allows that system to do work, and if that work is done, the energy in that system is lost. So then you can see the fact that whatever work is done corresponds to a change in energy of a system. And just like you and every day, I'm pretty sure, hopefully you have high amounts of energy level right now. If you do work like watching this video, your energy level is going to go down. So then more specifically, what is work? Work is a force times displacement times cosine theta. So let's quickly go over each one of them. You have force measured in newtons, displacement measured in meters. And this angle theta is the angle between the force vector and your displacement vector, measured in degrees. So what that is imagine I have a box that is being pulled by a force at a certain angle, and the box is moving forward with a displacement of s. The angle between F and S is this one that you see over here. So essentially what that is doing is I want to find the component of the force that is parallel with the direction of the displacement. The other components of the force is not doing any useful work in pushing this object forward in the s direction. Hence the cosine theta. In math, it's kind of like the dot product, but if you don't know what that is, ignore what I just said there. So going back to work, the units of work is, in terms of derived units, you might see that, and that just comes from the fact that force is mass times acceleration, which is kilograms times meters squared, and times s, which is displacement, that's another meters. Meters times meters gives you 2, and then seconds to negative 2, that's just seconds on the bottom. But most of the time, we are going to use this one over here, joules. No, it is not jewelry around your neck. It is joules with the units of J beside your numbers. And it is a scalar, not a vector. We often talk about how work is gained, how energy is gained or lost. It doesn't tell you which direction energy is going. Okay, so now you have a bit of understanding of work and energy, or at least what I want you to know before tackling these problems. I do example 1, you do example 2, while I put the solutions on fast play. So let's get started. Wakeboarding. Mikasa goes wakeboarding on an ocean where the rope she holds makes a 19-degree angle relative to the horizontal. If she feels a 680 Newton pull from the tension in the rope, and if she travels 340 meters, how much work would the tension force do after traveling that far? Anyone going wakeboarding? Fat Mama Physics jealous. All right. Let's start off with a free body diagram. We also know a few values here, which include the displacement, force of tension, and Mikasa's mass. In the free body diagram, I drew an FR, which is resistive forces, which include the drag forces and from the air as well as from the water. None of that is specified yet, comes in question B, but they do exist, so we should draw it in. Now here's the interesting thing, and this is what I want you to get out of this problem, is the fact that the question is asking for how much work would the tension force do. It's not asking for any other force, it's just asking for the tension force. So I don't need to care about Fn, Fr, or I don't even need to care about Fg. So the mass was not even needed. I don't even need the mass, because why? Work is just the force times displacement times cosine theta. And in this case, the force is the tension force. That's 680 newtons times the displacement, which is 340 meters. Cosine theta is cosine of 19 degrees. I put that in my calculator and voila. I get 218,603. And running out to 2 sig figs, I get 220,000 joules of work. That's a lot of joules. Next up, question B. We have Mikasa also experiences drag forces from the air as well as from the wakeboard breaking the waters. If the total resistive forces acting on Mikasa sum up to 330 newtons, calculate the work done by the resistive forces over 340 meters. Now we know what Fr is, which is the total resistive forces. We have the displacement, and the only thing we don't have is the angle. Now this is interesting because Mikasa goes forward. Her displacement is forward. The the resistive forces are in the backwards direction. So if we need to take an angle, that is this whole thing over here. And if you're thinking that's 180 degrees, you are correct. So let's write that down. Angle is 180 degrees, which then when we go to calculate the work, we have the force is 330 newtons. We have S is our displacement, 340. Cosine theta is now cosine 180. Now here's the interesting thing. Let's put in just cosine 180 and see what that gives us. And if you predict that's going to give us -1, bam, you are correct. That means I have -1 times 340 times 330. I get -112,200. And rounding up to 2 significant figures, that is -110,000 joules. Now you are probably thinking, isn't work a scalar, so then it doesn't have direction, so why do we get a negative sign? What does that negative sign mean? We have to go back to this diagram of the system over here. So then when we do work on the system, usually that causes the energy level to go up, which is probably what the tension force is doing to Mikasa in this case. However, if you imagine that the friction forces are taking away energy from Mikasa, causing her energy level to go down, that's one way to think about it. Or you can think about the friction forces causing the air and the water around Mikasa to slowly heat up due to these friction forces. The work done on the surroundings causes Mikasa's energy level to go down is another way to think about it. Specifically, the energy we're talking about here is kinetic energy, which is, we'll talk about in a later video, which is the energy related to motion. If it weren't for these resistive forces, Mikasa's energy level would be a lot higher given the same amount of tension forces. So that's what a negative work means. It takes away energy from your system. So 2 things I want you to grab out of these 2 examples. Number 1, make sure you read the question carefully on exactly what force do you want to use to calculate your work. The second thing that I want you to grab out of this video is the fact that don't be scared when you get a negative energy or a negative work. It just means that your system is probably losing energy as a result of that work. Okay, time for you to try this problem. Here I have Fat Mama Physics. I am dragging a 12 kilogram crate of board games across the floor by pulling on the rope with a force of 530 newtons. There's also 190 newtons of friction forces acting on the crate. After pulling 22 meters, calculate the work I did on the crate and the work done by the friction force. So pretty much a mirror of the previous question here. I drew a picture of myself. Anyways, Don't forget that angle. Good time to pause, and good luck. Okay, my turn to do the problem. So here we have the tension force directed at an angle 36 degrees above the horizontal, and the friction force directed opposite to the direction of displacement. The force of tension makes a 36-degree angle with the direction of the displacement, hence cosine 36. And that gives us a total of 9,400 joules. As for the work done by the friction force, we only use the 190 newtons. We don't care about the other forces. But that force makes a 180-degree angle with the direction of the displacement, meaning we have to put in cosine 180, which then makes everything negative, giving us negative 4,200 joules. Alright, and here are the solutions to the problem. So then in question B, if you just put a negative sign in front of Fs and not do the cosine theta as 180, that would have been correct as well, since the force parallel to the displacement is in the opposite direction, causing it to be a negative force. Okay, so here are the solutions. Very similar to the last problem. Hopefully you learned something from these examples that you can apply in your practices. I wish you good luck, and see you in the next video on force, work, and energy. Fat Mama Physics signing out with her board games.